Welcome to the Rossby Prize seminar. My name is Páll Holmlund. I'm a glaciology professor here at Stockholm University, and I'm also chairman for the National Committee on Geophysics at the Royal Swedish Academy of Sciences. I will start with a few remarks on the background to why we are here, and in a short while present the Rossby Prize to our honored laureate. This will be followed by the seminar on the role of geophysics in society. But Carl Gustav Rossby, he was a great scientist, academic leader, and through his achievement contributed to the safety of a growing population on Earth. After studies and work in Europe, he spent many years in the US developing the science of meteorology and methods for weather forecasting. The growing of air traffic in the time increased the demand for good weather forecasts, as he was one of the first to introduce computers for this purpose, and he continued this important work when he came back to Sweden. Carl Gustav Rossby explained the large-scale movements in the Earth's atmosphere that are today called Rossby waves. You see him here on the cover of a Time magazine with a weather map in the background. Rossby passed away in 1957, and a couple of years later the Swedish Geophysical Society founded a prize in his name for outstanding research in Nordic geophysics. Today, the prize is managed by the National Committee on Geophysics, and the members of this committee represent many aspects of geophysics on our planet and its surrounding. And we are also national correspondents in associations within the International Union of Geodesy and Geophysics. I'm greatly honored to now present 2024 year's Rossby Prize. Páll Einarsson, Professor Emeritus of Geophysics at University of Iceland. In the same spirit as Carl Gustav Rossby, he has both brought new knowledge and significance on geophysics to our society and for our safety. Rossby on how weather systems travel, and Einarsson how the Earth itself moves. The Rossby Prize 2024 is awarded to Páll Einarsson for his profound contributions toward advancing our understanding of geophysical phenomena, particularly in the disciplines of seismology and geodesy. Through pioneering applications of these disciplines to unravel magmatic and tectonic processes along the plate boundaries of Iceland and the North Atlantic, Páll Einarsson has not only expanded the frontiers of knowledge, but he has also nurtured the next generation of geoscientists through exemplary mentoring. The Rossby Prize 2024 seeks to recognize not only scientific excellence, but also the altruism and collaborative spirit exemplified by Páll Einarsson in advancing our understanding of geophysics and technomagmatic processes and their applications for volcanic and seismic hazards. So, Páll Einarsson, now I will ask you to come here. Congratulations. I think that you can come.
Okay.
Yeah. Now it's time to go over to the seminar for today, the role of geophysics in society. And therefore I hand over to my colleague, Professor Steffi Burchardt, who will lead the rest of the afternoon.
Thank you, Páll. Welcome to the Rossby Prize seminar with the title, The Role of Geophysics in Society. My name is Steffi Burchardt. I'm professor of tectonics at Uppsala University and a member of the National Committee for Geophysics. In the following about 2 hours, we will get some insight into the field of geophysics and particularly those areas that Páll Einarsson has contributed to. Geophysics is one of the earth sciences and studies the physical processes that occur within our planet on its surface and in the atmosphere. Today we focus on solid earth geophysics, a discipline that uses physical methods and principles to understand the planet's internal dynamics and structure. Solid earth processes cause phenomena such as earthquakes, volcanic eruptions, and landslides. And these phenomena can endanger humans and, in some cases, society. It is therefore not only necessary to understand and monitor geophysical phenomena and improve the methods for monitoring, but it's also important to communicate data and their implication to decision makers and the public. During the seminar, we will hear about geological processes such as earthquakes, volcanism, landslides, as well as the risks these phenomena cause and the role scientists play in communicating both the processes and the risks. Páll Einarsson will speak about the role of geophysics during volcanic and seismic crises, followed by a coffee break. Then we will have 3 speakers who will look at different aspects of geophysical phenomena. Björn Lund from the Swedish Seismic Network will talk about earthquake risks in a low seismicity country. Halldór Geirsson from the University of Iceland will look at solid earth processes that are influenced by climate change and melting glaciers in Iceland. And Rebekka Steffen from the Swedish Mapping, Cadastral and Land Registration Authority, also known as Lantmäteriet, will talk about climate impacts on seismicity. Each of the talks will be followed by a short opportunity to ask questions, but you're also very welcome to interact with our speakers during the coffee break. So thanks to our speakers, we will be able to explore solid earth hazards both in Iceland, a country with very active plate boundaries, and in Sweden, a country far away from active plate boundaries. We will also get a glimpse of hazards that are part of this planet and that humans cannot affect, and hazards that increase in magnitude and likelihood because of climate change. Before I hand over to our laureates, I want to thank the Royal Academy of Sciences and the Center for Natural Hazards and Disaster Science for their support in organizing the seminar. Páll, your turn.
Well, thank you both. It is not an easy task to start speaking after this introduction. I will try. We will see how things develop. And I decided that maybe the biggest contribution that we could do here at this moment to a wider community of geoscientists would be to expose our methods of communication between scientists and the people who have to live through the consequences of the events we are trying to study. And this is not an easy task, and I will just try my best to do this. To the outside world, Iceland looks quite ominous, to say the least. I put up here, first of all, a map of the earthquakes as seen from the outside of the North Atlantic Ocean around Iceland, just to emphasize the position that Iceland is situated on a plate boundary between two of the major plates of the Earth, and large earthquakes are quite common, and Iceland is a part of that. We are really sitting across this plate boundary, and this emphasizes that we are really living in an earthquake country in first degree, and in second degree we also have volcanism associated with all this, and not only just volcanism as is typical for the plate boundary in general on the ocean bottom. We are also sitting on a hotspot. Hotspot is the surface expression of a mantle plume where material is rising from deep within the Earth, as you see in the right side picture, and this causes extra volcanism in addition to what the plate boundary itself produces. And in fact, that is why Iceland is there. That's quite important to note. And otherwise, if we were not sitting on this mantle plume, Iceland would be just another piece of the plate boundary of the North Atlantic, and which is normally at the depth of 2,000 or 3,000 meters. So Iceland is there because of the volcanism. This is important to keep in mind, and I think that is one of the reasons why the general attitude towards volcanoes and volcanism in Iceland is very different than in most other countries. Most other countries tend to think of volcanoes as a terrible thing. They do really big and terrible things to people living next to them. But in Iceland, of course, the volcanoes can be quite terrible, but they are also the reason why Iceland is there. And there are some extra benefits that follow. And that is probably the root of the somehow, well, almost schizophrenic attitude of Icelandic towards the volcanoes. On one side, they really fear the volcanoes. On the other side, they also quite like them. And volcanoes are actually quite popular in Iceland. One of my earlier co-worker put this in words, and he said, well, a good volcanic eruption is the biggest public entertainment you can think of. And that is partly true, but on the other hand, we really have to live with the consequences of eruptions, and they can sometimes be quite hazardous. Okay, so when we look from the Icelandic side on the earthquakes, so here is an earthquake map. These are the epicenters of earthquakes during just 1 year. It's last year, and here you can see that there is quite a lot to this. In addition to being just a plate boundary, we can see here the plate boundaries for sure, coming from the north here and from the southwest into the island. But when it crosses the island, it's quite messy, and we can see this in some more detail here in the south here. The Reykjanes Peninsula, which is now the scenery of some of the most dramatic volcanic events that we have seen. And in the north, we see the Tjörnes fracture zone here, divided in two or more branches even, producing quite serious earthquakes from time to time. But then, in addition to that, we see here traces of an old plate boundary here, and quite a lot of seismic activity. And then we see these clusters like this one here, and this one here, and they actually are new. They have not really been very active in the last 50 years until in the last few years. And in both of these two areas, the seismicity is increasing year by year. So they are certainly one of the things we have to worry about in the near future. And if we go to central Iceland, to the center of the hotspot, we have some of the most terrifying volcanoes. For example, here the Bárðarbunga volcano right in the center of the hotspot, and the Grímsvötn volcano here. And these are probably our most active volcanoes, together with Hekla and Katla in South Iceland. So, well, I can't help telling a little story here, because when I sent in this presentation on, I think it was on Tuesday, I had to put a note with it saying that possibly by Friday this would be obsolete. Because on Tuesday, the Bárðarbunga volcano right here had a serious seismic crisis. There was a big earthquake swarm of the caliber that we haven't seen in the last 50 years, except in 2 cases, and in both cases it ended with an eruption. Well, that particular sequence ended very abruptly, and Bárðarbunga has not been heard since. So this is what we have to deal with. Just one example of how what kind of science we are doing. We are observing and we are collecting experience to be able to tell what the future brings. Well, I mentioned Grímsvötn as well. Grímsvötn is an interesting volcano because it has a big caldera, and that caldera collects water because there is a high geothermal activity in there, and every once in a while this water goes out of the caldera in a big flood, and we have just had one of those. So last week the flood started from Grímsvötn, and in some cases these floods have led to flash boiling of the geothermal activity in the caldera, and sometimes that also leads to an eruption. That kind of an event happened in 2004, last time, and yesterday it almost looked like that was going to be the case in Grímsvötn as well. So yesterday we had, or the day before yesterday actually, on Wednesday, we had a case of a possible eruption in Grímsvötn. Well, this time it only amounted to a flash boiling of the geothermal system, which is still going on. In that volcano, an eruption has not occurred yet. So this is just last week. And then yesterday, this area in Western Iceland, the one right here, also had the largest earthquake swarm it has had since this activity started in 2021. So, that sequence almost certainly has to do with magmatic movements in the crust, and it is escalating month by month. This activity is increasing. It would be nobody's surprise if it erupted in the next months or years. So it's one of these areas we are keeping an eye on. So in addition to the really spectacular activity on the Reykjanes Peninsula, last week saw uncertainty periods for 3 additional areas for volcanism. So this is the daily life of geophysics in Iceland, or should we say weekly case. So the hazards that are related to the position of Iceland on the planet can be divided into three branches. One is volcanic hazard. The volcanoes can actually do quite terrible things. We have 30 active volcanic systems on the island. They are not all active at the same time, and we have about half of them that have not shown no sign of activity in the last decades or so. So they are sleeping for a while, at least. So we don't have to worry about all of them. But about 15 of them we really have to keep a close eye on. Secondly, we have seismic hazard, and this is just earthquake hazards. That means we can have, because we are on a plate boundary, we have 2 active fracture zones within our territory that we have to worry about. Each one of them can produce earthquakes of magnitude up to 7. And fortunately, that happens only, well, maybe twice a century or so. But we have magnitude 6 earthquakes and magnitude 5 earthquakes that can actually do quite a bit of seismic damage. So seismic hazard is certainly something we have to worry about. But in addition to that, we have what is the third kind, which is surface fracturing. And surface fracturing can, of course, cause earthquakes. But the biggest surface fracturing, however, is caused by diking. That means magma that is trying to erupt but doesn't quite make it to the surface. And but it causes fracturing at the surface. And in the previous activity we have seen in Iceland, including the presently ongoing activity on the Reykjanes Peninsula, it is really surface fracturing that has caused most of the damage that is already there. The evacuation of the Grindavík town, which is a town of 3,600 people, if I remember correctly, it was evacuated on the 10th of November in 2023, and that was almost entirely just because of fracturing, not because of the earthquakes, not because of the volcanism. It was because of the failed volcanism, the volcano that didn't erupt. And it caused fracturing of the ground, and the fracturing of the ground ruined a lot of houses and made the town just dangerous to live in for a while, and still is. And that is mainly due to this first dike injection. So we have to classify that as the third kind of geological incident in Iceland. This is a message that we have difficulty conveying. This was really a message, a lesson we learned during the 70s and 80s of last century in the Krabla activity. And this was put into the regulations, building regulations and so on. But the builders didn't quite believe us, and they continued building Grindavík, cross fissures, and almost all these houses are ruined now completely. They have to be destroyed. Okay, so how do we convey this information? And there are several snags here that we really need to be aware of. So living on a hotspot includes a lot of these natural hazards, and the natural hazards are studied by the science community. And but the people who have to suffer from this are in the public community. So how do we get this information across? And in most countries, it goes through the authorities in some way or another. In Iceland, it goes through the civil protection, which is a particular branch of the authorities, or through the politicians in politics. This information is conveyed. And then, of course, the media, just the public media. This causes problems. And the main problem is the long response time. To bring this information through the civil protection or the authorities takes time. And usually when something like this happens, this time just isn't there. And the media react slowly. It takes at least a day or two to get the most important news on the newspapers or on the radio news and so on. So there is a long response time. And then there is this really fear of panic that seems to be quite widely distributed in the world. And well, you don't have to see many catastrophe movies to see these problems. The politicians, they like to keep things quiet if there are problems. Authorities don't want to cause panic in the community, and the public community is unprepared. They don't really know how to handle it. When you distribute news about a coming eruption or a coming earthquake, the public generally is not prepared for that. And it does cause panic in some cases, or at least unreasonable reactions. And the most difficult part is this lack of trust. Because of this fear of panic, the authorities tend to keep these news secret. Politicians definitely want to do that. So there is this tendency to keep things secret. And I think this is probably inherited from the military background. Military secrets are known, and you don't want to tell the public everything that you know. And this causes lack of trust. So the public doesn't trust the authorities in these situations. And the authorities don't trust the public for the information. So there is a lack of trust, which is a problem here. Which means that even though we scientists think we know something, we may be able to predict some of these things, there is lack of trust, and the public community is not prepared for it. So that may sound like a lot of our work is in vain, that we are not really doing any useful work, if that is the case. Well, these problems, I think we have at least partly solved in Iceland, and we do it the Icelandic way. So we just bypass all this jungle of information flow. And there is, since a long time ago, there is a direct link between the science community and the public. And this just, well, it's not a recent thing, and we are not responsible for it here in this room, but that's just how it is. And this means we prevent this lack of trust that is between the scientists and the public community. And actually, this partly has to do with this, what I mentioned earlier, about this popularity of the volcanoes. This really is transmitted onto the scientists who are studying the volcanoes. They are actually, in many cases, quite popular. And our best example of this is, of course, Sigurður Þórarinsson. He probably gave lectures here about 70 years ago in this building, or he was a member of the Swedish Science Society. So, and he lived in Stockholm for several years. He was one of the most popular person in Iceland during his time, and not only because he was an interesting guy. He was a poet. He wrote popular songs, and he had this ability to convey his science to the public directly, without any intervention of the politics or authorities. So this is, I think, what well, it's one of the main messages of this talk is this, that I think we have at least partly solved this problem of trust between the public and the science by direct communication. We just don't care what the politics says about it and the authorities. And there are several things that we do to do this. And one is, nowadays, there are some very popular web pages where everything is put, all significant results of the measurements that we do, of the understanding that we think we have. This is put on the web pages, and one of the most popular web pages in Iceland is the web page of the Meteorological Office, which has the earthquake map updated every 10 minutes. It has all significant results put on it, and the media, they take their information from there, and so on. And our institute at the university similarly has a web page where everything is put. This is very important to be able to say if some mistrust comes up, which inevitably it does. We can say, well, just check for yourself. It's on the web page. There are no secrets. This is very important that we can maintain this claim. There are no secrets, and everything is on the web page. So if you don't trust us, then just have a look for yourself. And we also make sure that some of this is also conveyed through the media. The media are, of course, very good for distributing information and understanding. So, well, the state of the volcanoes is a very popular discussion theme in all parties and all meetings and everything. The volcanoes are really popular. So the public is prepared. And a good example is this evacuation of Grindavík on the 10th of November in 23. Actually, the evacuation started before the order was given to leave the town. The people just knew by themselves. This was the time to visit a friend somewhere else. And so there was a big exodus of people leaving Grindavík quite a bit before the order was given by the authorities to do so. So I think we have at least mastered some of these tasks. Well, then, how do we do this? We have to be sure that everybody knows how we define, what are the definitions of the terms that we use. We have to make sure that this gets across to the public. The Icelandic language helps us. Icelandic language is a bit different from most other European countries because we don't use old Latin words. We don't use these technical terms that are so frequent in, for example, English or other things. We make the general demand that we make Icelandic words for things, for terms, and that these words are transparent, that they describe themselves what they mean. So we have all kinds of interesting words for things that in other European languages have a Latin word that nobody understands, really. So it helps us. But we will go through the definition of monitoring and what we mean by forecasting, what we mean by prediction of an event, and then warning. These are different stages of this process of conveying a difficult situation to the public. You have to be sure that what you're talking about. Well, it's good to talk about this here under Rossby, and because the weather forecast is really ahead of us there. Most people understand what a weather forecast means, and nobody makes the absolute demand that it's a precise prediction for the weather tomorrow. We know, most of us, what it means when a weather forecaster says, well, it's likely to be a storm tomorrow because there's a low coming, and so on. We know this, and we can almost make the prediction ourselves most of the time. So this is important. So But the methods we have to talk about the world below us, it has to go through instruments. Sometimes this instrumentation is complicated, but in simple terms, you can explain most of this to the public. What a seismic station is, for example, and what the GPS. Everybody in Iceland knows what the GPS is, and the INSAR is a term thrown around, and most people know what we mean by that. And so we use seismographs to measure the oscillations of the ground, and we use GPS and the tilt and the INSAR pictures to tell how the surface is reacting to what's underneath. And when we put up an INSAR graph on the television screen, most people know what that really means. So these are the methods that we have to tell what is happening under the surface. And so this is the way to convey this. And then I will give a short summary of our successes and failures of issuing warnings. The final step in this process is to issue a warning to the public. And this is done through radio or whatever is needed to do this. And sometimes we are right, sometimes we are wrong. Sometimes, while the warning is usually, we have the weather forecast as a goal to reach. Sometimes our forecasts are wrong. Sometimes it is bimodal, or many scenarios possible, and we try to convey this to the public as well. What are the insecurities about what we are saying? And most people understand that we are not demanding absolute prediction, exact position of something happening or exactly what's going to happen. We are trying to narrow it down, what kind of an event we are talking about. So, and then finally I will give a short overview of what the status of the different volcanoes is right now. So eruptions are frequently preceded by underground movements of magma. So the fluid is approaching the surface, and it causes deformation of the surface, and it produces earthquakes, and both of these things we can measure quite well. So we have seismic methods to do this, to pinpoint what is happening. It's usually the first step to select what volcanoes do we really have to monitor and which ones are not doing anything. We have deformation measurements that are usually bound to a certain place. So usually that comes in after the seismic methods. But now also we have the INSAR pictures that also give us a map of the whole thing. So there is certainly big progress being made in this. So deformation measurements tell us by model calculations approximately what's happening on the ground. So in geochemical methods, we can, in some cases you can measure the chemistry of water or chemistry of air coming out and so on, and that will tell you something about what's happening on the ground. Here is a good overview of the definition of terms. Monitoring, that means observation based on measurements of significant parameters for state of the volcano. So it gives you a way of telling what the volcano is thinking. So forecasting then is about a statement about the likely future development of events on a volcano. And that is a difficult thing to do because a volcano is really a very versatile beast. It can do many different things. And but when you know what the status of the volcano is right now, you can more or less guess what are the likely scenarios that can develop from the present situation. So the present situation is the key, and then you can, well, depending on your imagination, how many scenarios can you make up for that. And then prediction, it is really a term that we very rarely reach, and that's a specific statement about future events, stating the kind of event, the size of it, the location of it, and the time, when will it happen, and with uncertainties, of course. So this is a really quite a precise parameter that you need to be able to predict. In some cases, we can actually do that, but in most of the cases, we just have to wait until the final warning comes, and then we give a warning to the public. And this could be an earthquake swarm, a sudden movement of the ground that's unexpected, or something that really happens on your instruments. So these are the different terms, and it's quite important to make a distinction between these different steps in the process before you issue a warning. I put up here a good graph of one of the parameters we have found that is very describing for the situation. This is an elevation of a point near the center of magma accumulation on the Reykjanes Peninsula, where the magma is really coming and accumulating before it erupts to the surface. And we found this found this point by measurements, and we can see the story that is still going. We can see here this is up, moving up. So these are months here. So this is the beginning of the inflation of this magma system of Svartsengi. It really started quite suddenly right here, and could be spotted right away. And then the pressure increased until finally the storage area couldn't take it anymore, and the magma burst out of it. And there was this big dike. A dike is really a magma-filled fracture that propagates in the crust. And the crust couldn't take the pressure anymore, and magma was injected into the crust. And this dike went right under the town of Grindavik. And this is really the event that caused the damage in Grindavik, this first one here. And the magma chamber collapsed several tens of centimeters, and the dike stopped at one point, and immediately the ground started rising again. So magma started flowing into this magma storage right after the dike stopped propagating. So, and since then, this has been happening. It's still happening. And so this curve is really like a pressure gauge on the pressure of the magma chamber in the crust. And there is a remarkable regularity to it. And this regularity can be used to forecast. And you can see, for example, one rule that has very rarely been broken is that the pressure in the magma chamber has to exceed the previous maximum. You can see that. It really takes, when you put a dike into the crust, it increases the strength of the magma chamber. It takes a higher pressure next time. So every time it happens, it requires a higher pressure. And this offers us a very useful way of prediction, or forecasting, should we say, because it allows us to forecast the safe period. So we cannot really predict or forecast when it will break again, but it will tell us the time when it definitely will not break. So it gives us a forecasting way for safe periods. So this is really very important. So here we, right. So we can forecast the safe periods. The safe periods are there. And for people living in the area, this is really a very useful forecast. So not being able to forecast exactly when it will erupt next time, but we can give them a safe period where they can live their life, they can do things that they normally do. So this is a very important forecast. Okay, another way we can look at things is through what we call volcanic tremor. Tremor is usually in seismology used for the phenomenon when the ground really oscillates continuously. And this happens quite frequently. We have different types of tremor. We have wind tremor, we have surf tremor, we have anthropogenic tremor, cars and things like that, and we have microseisms here. And they are special kind of tremor that are caused by the swell on the open ocean. So the North Atlantic Ocean, with its bad weather, produces a lot of microseisms, so-called. And this is really what determines the sensitivity of seismographs. So this is really that determines how small earthquakes we can see on our seismographs. So it depends a lot on weather. And there is an interesting, okay, but we also have tremor that is associated with volcanoes. And here is a tremor graph. It's a graph that gives us, as a function of time, gives us here the oscillation of the ground. We see the high frequency oscillations here, the blue curve. Green is intermediate, and the red one gives us the low frequency of the oscillations, mostly sensitive to these microseisms of the ocean. So here is for the Grímsvötn volcano. It's a very valuable thing. We can actually define. We can define three kinds of tremor here, and these are water tremor. Grímsvötn has these jökulhlaups when water flows out of the caldera. That is the blue curve here, and then we can see here something happening suddenly, and this most likely has to do with this flash boiling of the geothermal system. So this is geothermal burst of tremor that you see here, and it remains after the flood is gone. So we can see at least two kinds of tremor here, the water tremor and the geothermal tremor. But then occasionally we also have eruptions happening in the volcano, and sometimes these eruptions are triggered by the floods. So when the water goes out of the caldera, the pressure decreases on the magma underneath, and it decides to erupt. And we can see a case of that right here. We can see the water tremor here, and then suddenly everything goes crazy right here, and an eruption breaks out here. And you can see the red curve here goes up much more than in the previous ones. So we can see here the third kind of tremor, that is eruption tremor. And but then eruption is over here, the flood is over here, but then still we can see the geothermal tremor right here. When there is only an eruption in Grímsvötn, that also happens. That happened in 2011. You don't see a water tremor here, and the eruption starts, and the tremor goes up. The eruption stops, and all the tremor goes away. So we don't see water tremor, and we don't see geothermal tremor, only eruption tremor. And in fact, because I mentioned already that we had a jökulhlaup from Grímsvötn this week, it was this kind of an event that we saw. The red line doesn't go all the way up to the other lines, as it does here in an eruption. And so this is just a jökulhlaup and the flash boiling of the geothermal. So this is really quite important to be able to interpret these measurements of continuous things. Sometimes there is just no question. We don't have to worry about anything. This is really the precursory activity prior to the eruption of Hekla in 2000. And we can see here the seismogram. There is hardly anything happening right here. 10 minutes later, there's lots of earthquakes. And every 10 minutes here, the earthquake activity increases. And then finally, the eruption breaks out. So this is a specialty of Hekla. It has a short precursor, erupts basically without any warning, or with very little warning. Opposite to the Reykjanes Peninsula, here we see something similar for the Reykjanes Peninsula. Here are the, this is February March of 2021. First eruption of the 10 eruption sequence that we are still in the middle of. And we can see here, these are earthquakes. These earthquakes have been going on for 2 weeks until finally the eruption broke out. And as soon as the eruption broke out, the earthquakes almost stopped. But the tremor went up from here to here. And then this eruption lasted 6 months. And the tremor was really the best monitoring method to find out what the volcano was doing from day to day. Okay, here we have an interesting connection. This is the latest eruption of the peninsula, and we can see the beginning of it on here. So this is a month here, this is October before and November, and we see this on 4 different stations. Here is the beginning of the eruption. The tremor goes from here up to here. So you can see it on this station as well. Here goes up to here. But there's a lot of things going on. And we better know, be able to put a name on what is all the rest of this thing. And so, well, we'll come to that. Here is another one of these that happened this autumn. This is a station on the rim of the Katla caldera. Katla is one of these really very difficult volcanoes in South Iceland, and it hasn't had a large eruption through the glacier since 1918. So, but it's really a very dangerous volcano. So here it is. Something important happened. There was a flood from the caldera at the end of July. And you can see that here. This is a water flood, tremor going up here, and then just dying out. But you notice also the purple line, the low frequency, goes up with it. Goes up as high here. So if we use this to compare to Grímsvötn that we just saw, this would indicate that there actually was a small eruption into the glacier at the same time. It was triggered by the flood, just as we have seen in Grímsvötn. Well, we are still debating this. There is no general agreement on how to interpret this. I am, as a seismologist, quite convinced that there was actually an eruption, but I must admit, some of my colleagues don't agree with me on this one. So, but as we see here, there is a lot of things happening. Also here, we see into October, there were actually four small jökulhlaups that followed the main jökulhlaup, and we can see those here in the fracturing. There is increased fracturing here in the caldera associated with these. So, and these came from the same area as the big one here at the end of July. But the purple line did not react on these ones. So these were probably just hot material that was produced by the initial eruption, was melting ice and producing these regular floods afterwards. This has died down since then. So you can have a look at these. These are really important sources of information of how the Earth is behaving. And if we just go one more, we can also see we can see storms on here. right here, and this, that's when the wind in Iceland, the famous wind of Iceland, is really shaking the earth. But there are other things that are also happening here, and now we get to the important connection to this meeting, because I must admit I had to Google Rossby, and then you read everywhere, Rossby invented Rossby waves, of course. And these were waves that are between hot and cold air masses. Here, this is from a textbook in meteorology. It's a jet stream and the wave action on the jet stream causing low pressure systems that travel across the from west to east. And if we look at just a random weather map of the globe, you see something like this. This is from January 10th. Now you can see a string of these lows right here and here. These are really the expressions of Rossby waves that we see here. At the end, you see where Iceland is located, right here in the middle of this stream of lows. And actually, we have in Iceland a word for this. This is called the lægðagangur. There's usually a row of lows just waiting to bother us, and with bad weather, rain and winds and all that. And this is really the worry of seismologists, because this really determines the sensitivity of seismographs in Iceland. That's why Icelandic seismographs are really not very well located. It's not an easy way to conduct seismic observations in Iceland because of these waves. So do we see those? And actually, in this time series that I showed, you can see the waves on this here, on the purple line. This is really the amplitude of the low-frequency microseisms on the Atlantic Ocean. So I think, as far as I know, this is the only time Rossby waves have been demonstrated on a seismograph. So here you are. Okay, it seems that our time is really running out. Yeah, okay. So we have to be quite quick on this. I have to tell you one story though, and that's about this knowledge or understanding among the Icelandic public about volcanoes. How long back in time does that actually go? And we have an idea about that. So what did Icelanders think of lava flows, for example? And this is the latest eruption of Reykjavik. This is a picture taken in November. And so Icelanders' long story of living with these volcanoes and lava flows. And the oldest story you can take up is from the sagas, actually, and it tells the story how Icelanders became Christian in the year 1000. The year 1000 was an important year because there was a widespread rumor in Europe that this would be the end of the world. And therefore it was considered quite important to turn everybody to Christianity before that, just to secure their place in heaven and all that. So there was this discussion in the Parliament of Iceland at Þingvellir in the year 1000. Yeah, and it was discussed. This discussion whether Icelanders should turn Christian, and because before that everybody was heathen. There were a few Christian people, but it was really discussed seriously whether Iceland should officially turn Christian at this point. this discussion got quite heated, and people were divided, and people were ready to fight about it. There were weapons around. And so then the news came to the Parliament place that there was an eruption, and lava flow was flowing towards several farms and destroying farms. So then everybody got very excited, of course, and there was this thing, no wonder the gods are angry at us, discussing this outrageous idea. That was really the line there. Then Snorri Goði was one of the chieftains in the area from West Iceland. He replied to this with this really remarkable sentence. He said, "To whom were the gods angry when the lava burned that we are now standing on?" This was really the key question, and everybody saw the sense in this, this question really settled the argument, and the conversion was adopted peacefully. They saw that it was quite unlikely that any gods would do such a thing as this. And what was the argumentation? Well, you can draw two conclusions that the people at Þingvellir understood that they were standing on a lava flow. There is actually an old lava flow there. And they realized that what was happening now was the production of a new lava flow that was just like the one they were standing on, which was definitely put there before they were there, before any people were there. And this was obvious to anybody. So this was clear to everybody how lavas were formed. And this is quite remarkable because it was still about at least 500 years later. It was quite unclear to educated people on the mainland Europe how lavas were made. And there were the Plutonists that had this opinion that this had something to do with volcanoes, and there was the Neptunists that thought that these were just hardened sediments. But the story from Þingvellir tells us that everybody in Iceland was quite clear about how lavas were formed. And also that since there were no people when most of these lavas were produced, it was very unlikely that God had anything to do with this. At least he was not angry to any people there. Or at least it was very unfair if he was putting the lava in the wrong place. So you can draw three conclusions from this. Also, that this argument was not only clear to the leaders of the people, not to the educated people. It was obvious to everybody, not just the educated. So this is quite important, that there was widespread knowledge about lava flows and how they were made in Iceland already in the year 1000. Well, the historians argue. They are still arguing about the story. They argue, well, there are people that say, well, this is a true story. These things actually happened in the year 1000 at Þingvellir. And then there is this other school that says, well, it is probably just a story that the story writer wrote. But either way, I gave you a time limit of 500 years. It could be 1,000 years. So at least this story would make any sense in the 13th century when the story was written, unless this was also the case then. So whether it was in the 13th century or in the year 1000 doesn't really matter for this argument. There was a general understanding of how lavas were made, and it probably didn't have anything to do with God. So what would be this eruption? Well, there is a big lava flow in West Iceland, Hallmundarhraun, about 4 cubic kilometers of lava that flowed in the 10th century. So Snorri Goði probably saw this one, and so on. So you can quite well argue that. There is also the Eldgjá fissure that erupted in 934 to 38 or thereabouts. Very large, 18 cubic kilometers of lava. So Iceland has definitely had experience about this. Okay, we will go from this. Well, this was just to introduce the concept of stopping lava flows. And this is from Reykjavik Peninsula. There has actually been quite remarkable experiments with diverting lava flows in the area. You see the town of Grindavík right here in the background. And there have been lava flows coming into the town and so on. So diverting lava flows is a big thing in Iceland now. Okay, to give a short account of eruptions, how frequently we have eruptions to worry about. And if you just look at the time since 1970, we can count easily 32 eruptions in 55 years. So that is approximately the frequency. And then in addition to that, we may have some subglacial eruptions that are not generally accepted in this account. So here is, well, let's see. Okay, yeah. Here is an account of how successful we have been to issue warnings prior to some of these eruptions. So there's a list of eruptions here. The list doesn't really matter by itself. But you can see here, this column tells which eruptions were actually warned against. In which eruptions did we actually issue a warning of a coming eruption before it actually happened. And so you can see that this list is really quite densely occupied. There are some cases when there was a near warning, but there was a warning, but the eruption was already in progress when the warnings was issued, even though nobody had seen it. So the failures are really here when there was really nothing to be seen. And here is a list of precursor time. That's the time from the first indication on a seismograph that an eruption might be coming, also looking in hindsight. So, and then until the eruption started. And you can see this is a very varied list. The short precursor times are really here. These are where this is less than 1 hour before the eruption. The longest one before, including and ending with the Bárðarbunga eruption in 2014, is here, and it's 13 days. From the time we see an earthquake swarm and a propagating dike. So 13 days here, and then these are the short ones, and then everything in between. So there is quite a distribution. This is a very valuable lesson when you are really looking at something that looks like a precursor to an eruption. Then the next question is when? When is the eruption? And we must admit we cannot really say. This really varies quite a bit. And here we have 13 days as the maximum. During these 13 days, the whole nation of Iceland was following this story because the dike was propagating. It was propagating from the volcano underground and under the glacier, and it was making a progress every day. And then finally, when it got outside the glacier, about 45 kilometers or 50 kilometers away from the volcano, it finally erupted, quite a distance away from the volcano itself. And this took 13 days. But the public was following this every step of the way. The short one short one, the short-tempered volcano is Hekla, as I mentioned before. Hekla is quite explosive. As you see here, this is the 1980 eruption here. This column rose in several minutes up to airplane altitudes, and the precursor time for all known Hekla eruptions is very short. The longest one was the 2001, 79 minutes from the first earthquake until the eruption started. It has been shorter in all the previous ones, down to 23 minutes. So Hekla, besides being dangerous, it's also short-tempered. It really erupts in a very short time. Now, the ongoing eruption sequence on the Reykjavik Peninsula is here, 10 eruptions. And we see here the precursor times. So the first 3 eruptions occurred in the Fagradalsfjall volcanic system. Here we have 23 days in the first one, 4 days for this one, the second, and 6 days for the third one. Then it shifted to another volcanic system, the next one, this Svartsengi system here. And in this case here, these precursor times are all much shorter. So in this case, we really have to be very careful because precursor times of eruptions are very short in what we are still. We don't expect a long precursor time next time. And well, of course, you might question, when is the next time? And from the safe period graph, we can say it's very unlikely before the end of this month, but coming February, we are moving into times of insecurity there, and an eruption might be expected any time. So, here we have the state of the volcanoes, and I guess I would just have to leave that to you and to read through this list. This gives you what volcanoes are doing something and what they're doing. You can see here inflation is going on several volcanoes, and we have deep intrusion going on here in Ljósafjall, that is here, and in some cases we have inflated volcanoes that have inflated to the dangerous level, but are not doing anything. They are just continuing inflating beyond the safe period. And that includes Grímsvötn, it includes Hekla, Askja, we don't really know, but yeah, these are really the ones that are inflating beyond the safe period. Okay, and that concludes my contribution today. Thank you.
Okay. So, I'm Björn Lund, head of the Swedish National Seismic Network, and I'd like to thank the Rossby Committee for inviting me to give this talk. Although talking about earthquake risk in Sweden after Páll's talk is slightly daunting, I must say. And, you know, Páll talking about big earthquakes and these enormous volcanic eruptions. I was just going to say that we do have volcanoes in Sweden too. But even for us geoscientists, they are pretty old. With 100 to 200 million years ago, these were last active. So they're not quite as exciting as the Icelandic ones. But if we instead move over to earthquakes, we do have them. We actually have one earthquake in our neighborhood that was magnitude 6 or larger. This is a 1929 magnitude 6.1 earthquake. Probably. I'm sure that the magnitude of this event is quite difficult to determine out there in the ocean. So we have to go to slightly smaller earthquakes, and these are the recorded events since 1375 of magnitude 5 or larger. And as you see, most of them occur on the coast or outside of Norway and in Norway. And there's actually no record of an onshore earthquake in Sweden that was magnitude 5 or larger in the last 650 years, which tells you something about the hazard or lack of seismic hazard in Sweden. But the Lurøy earthquake in Norway, so this occurred up here in Lurøy, just on the coast basically. This is the largest earthquake that's been recorded in the Finno-Scandian region and around the Baltic, including northern Germany and Poland. And an earthquake of this size has actually felt through much of Fennoscandia. So there's actually shaking in Stockholm. It's reported from this very place, or at least this organization, that the Academy of Sciences felt the earthquake. And as you see, it was felt through Finland all the way through Norway and further south. And the intensity, the shaking at the epicenter was quite severe. So to the extent that if this earthquake would happen again today, I'm sure it would cause quite some damage if it happens in a populated area. We also have anthropogenic seismicity, and a lot of it in Sweden. So the mines, especially the two underground mines in Kiruna and Malmberget, are extremely active. So the extraction of ore at almost 1,000 meter steps creates lots of small earthquakes. They produce daily magnitude 1 to 2 earthquakes. And actually in May of 2020, there was a magnitude 4.2 earthquake in the production areas of this mine. And they were just very fortunate that there was no casualties. This was just 2 hours after the blasting, so there was nobody really in the mine at this time. But had this happened 5-6 hours later, there could have been some major damage and loss of life. But I'm not going to talk about anthropogenic events today. We'll focus on the natural earthquakes. So having seen these pictures, do we really need to worry about earthquake risk in a low seismicity country like Sweden? And I'll hope to show you that we actually do, at least in some instances. If we go back to the map, now just to keep you awake, I'm changing color of the big events all the time, so they're now yellow. And the red ones are events between magnitude 4 and magnitude 5. And if we look at this list, sort of, which is close to Sweden at least, we had the Kattegat event of 1759 here, which has been interpreted to be about magnitude 5.6. The Lurøy in 1819, 2 earthquakes in Norway in the 1800s, the Koster Island earthquake here in 1904. This was actually also felt all over Norway, Sweden, Denmark, much of Finland, and they reported it felt in St. Petersburg even. So the crustal conditions here transmit seismic waves very well, so the earthquakes are felt in far away, even though they are not that big. And if you look at the list, you see that including the Kaliningrad event here in 2004, we seems to have roughly 1 magnitude 5 event every century, at least in the neighborhood of Sweden. And if we then extrapolate that to a magnitude 6 earthquake, we would expect to have somewhere between 1 and 2 magnitude 6s every 1,000 years, and maybe 2 magnitude 7 events every 10,000 years. If we can have events or earthquakes that big, that is. So short time scales, not that many earthquakes. Longer time scales, not many, but we might need to actually think about them. So for regular buildings, we talk about building and building codes. Sweden does not have any building codes for earthquakes. And Sweden is actually the only country in the European Union, together with Finland, that has not implemented Eurocode 8, which is the European building codes for earthquake resilience. And the Swedish National Board of Housing, Building and Planning, Boverket, they consider that we build well enough for snow loads, for vertical loads, and wind loads in terms of the horizontal. I'm not quite sure I would agree with them that that's enough to prevent the horizontal motion in an earthquake, but that's the way it is right now. And since the sort of expected lifetime for most buildings are between 50 and 100 years, actually 50 years is used generally in building codes, with the seismicity that we have observed, well, maybe the hazard isn't all that large, or the risk to the buildings. But we have other buildings. We have critical infrastructure. And unfortunately, this map isn't great, but it was the best I could find. All these little dots are dams, and the red dots are the class 1A dams. Those are classified as if they rupture, there is major loss of life and damage to buildings. And for those of you who have read Mikael Niemi's Fallvatten, you know what would happen if the Sorva Dam and the upper part of the Lule River If that dam goes, all the other dams in the river goes. This river system provides 10% of Swedish electricity through the hydroelectric power, and the city of Luleå would be completely flooded. And dams these days have to consider risks on the size of 1 per 10,000, so 10 to the minus 4. And that basically brings us to these magnitude 7 events. There are possibilities of big events at that risk level. We also have the nuclear power plants in Ringhals, Oskarshamn and Forsmark, and we have the coming, both the high-level repository, which will be built in Forsmark, they start building in a couple of years, but also the low-level repositories in Forsmark. And there we have even longer time perspectives. We actually need to consider risks up to 10 to the minus 5, 10 to the minus 6. And then earthquakes is, of course, an integral part of that risk assessment. If we look at what we actually detect these days, the Swedish seismic network was significantly expanded between 1998 and 2010. So today we have 68 stations from Veberöd in the south up to north of Torneträsk in the north. And in the last 25 years, we've recorded about 13,000 earthquakes. I'm happy that Páll didn't mention the number of earthquakes they've recorded in Iceland in this time period, because again, this would show that we have much fewer. And of course, the ones that we observe in Sweden are generally much smaller. As you can see, I changed the color scale again, so now the blue ones are the 4s, and the red ones are smaller, and the little black ones are below magnitude 2. But we record about 2 to 3 earthquakes in Sweden every day with the seismic network as it stands today. And you see the distribution of earthquakes here. We have these events that are occurring along the north coast up to this area here, where there's south of Skellefteå. It's the most seismically active area in Sweden at the moment. And then we have these sort of streaks of earthquakes. We'll get back to those in a second in the north. There's also quite a lot of seismicity around the Lake Vänern area and along the west coast here. So if we want to do hazard assessment, we want to figure out how dangerous is it really with the earthquakes in Sweden. There are a number of issues that are more difficult perhaps here than in an area where you have lots of bigger events, because then there's no doubt that this is an earthquake, for example. Here we have to look very carefully at the data. Is it an earthquake or is it something else? Nowadays we're pretty good at figuring out that this is an earthquake and this is an explosion, so there's not that much explosion contamination in the data anymore. But if you go back, there's much more difficult with all the mining operations that's been going on in Sweden for centuries. You know, mine collapses have sometimes been interpreted as earthquakes because it shakes. If you look at the older data, the temporal distribution of data, you see that earthquakes in Sweden are much more common in December and January than any other month. And this is of course incorrect too, because these are frost quakes. Especially in the late 1800s, there was a period with lots of cold weather. When the temperature drops from above 0 to minus 10, minus 15, the ground tends to crack, basically. There's noise and there's shaking. And in 1894, we had a magnitude 5.1 earthquake in the catalogue because there was cracking of ground both in Sweden and Finland the same night, the 2nd of January 1894. But that's, of course, today we know that the magnitude 5 earthquake would not crack the ground in Sweden and in Finland. That's way too far. But all this shaking was sort of making the big event when they were associating them to each other. So we have to do classification correctly. We need to estimate magnitudes for the small events. And this is a bit of a tricky issue to get a small event magnitude, so the size of the earthquakes, to be consistent all the way through up to the big ones. We need also to figure out, you saw the map earlier, we know where the small events occur, but do the big ones actually, do they have to occur in the same place as we see all the small activity? I'll get back to that in a second. We have the ground motion, so how does the seismic waves travel in the Swedish crust with distance? If the earthquake occurs here, how much is the shaking here for a certain magnitude? We know for small earthquakes we have lots of data to look at, but for the biggest earthquakes we really don't have much data, and very rarely close to the big earthquake. So we don't have a good handle on these attenuation, the damping of the crust. And then, of course, how large can the large earthquake become? And if we just look at this issue of the location of the big events, you see the central map here, we see the distribution that we saw on the earlier map. But the big ones don't always occur there. We have, of course, the Kaliningrad earthquake is the biggest anomaly. There was basically no seismicity in this area for hundreds of years. And then suddenly there are 2 magnitude 5 earthquakes separated by about half an hour. How would we predict that or forecast that to happen? We have the biggest one that we've registered in the Swedish network since it was expanded, the Sjöbo earthquake in 2008 in Skåne, right here, magnitude 4.3. And maybe even more strange, this guy here in Lillhärdal in 2014. You see again, this is all the seismicity that we've been detected, and there's hardly anything in this area. So these surprise events is something that is very difficult to bring into at least a probabilistic seismic hazard assessment, where you look at the data or the earthquakes that have already occurred. But we did work together with a PhD student who finished about less than a year ago. We have constructed a new seismic hazard map for Sweden, where we see that the hazard is, fairly large up in the north, and that's all these events that we saw in this area. And why is that? Well, we have had very large earthquakes. So this is the Pervi fault. This was an earthquake that occurred just when the ice disappeared about 10,000 years ago. It's a 160-kilometer long fault parallel to the mountains west of Kiruna. And in northern Fennoscandia, we have a number of these faults. You see the really big offsets. This part of the rock has been pushed up against the other part here. It's the same. This is north of Kiruna. Really big post-glacial earthquakes, magnitudes 7 to 8. And they're still active today. So all the seismicity that we've recorded up in the north, the black lines show the surface expression of these faults, and the red ones are the earthquakes that we have detected. So they are definitely active. But can they happen today? Do we need another glaciation, a big ice age, to have enough stress accumulated in the crust for these earthquakes to happen? That's a bit unclear. And it's also unclear, if it were so that it could happen today, then of course hazard in this area, especially where we have these dams in the Lule River, would be significant. And trenching, digging into the fault here in Norway just recently showed that there was probably a magnitude 7 earthquake there only about 600 years ago. And that completely changes the thinking of these post-glacial faults, that maybe we actually don't need another glaciation. Maybe we could have one on the Pervi fault or on the Burchardt fault here south of Skellefteå today that was as big. So we're discussing this with the stakeholders, with, of course, nuclear power companies, nuclear waste company, also with the hydroelectric dam regulators. And we think it is really important that you do an assessment both in the probabilistic way, but also deterministic. We have to look at these faults and say, okay, what happens if a really big earthquake occurs here? How much shaking would you get then on this dam or in this mine which is close by? And not only look at what happened in the relatively short time period that we have actually been recording earthquakes. And then I just wanted to finish with a couple of slides to say that we're not only detecting earthquakes in Sweden in the seismic network, we're also doing monitoring of global earthquakes. So we provide the risk assessment here to the government crisis group in Regeringskansliet, basically saying that, well, big earthquakes, if they're green, they're not dangerous. If they're yellow, we think that there could be casualties and damage, and red, I'm sorry, but we know that there will be big problems. So this is the Tibet earthquake that occurred here some week ago, so that the government is ready and does not stand completely unprepared as they did in 2004 after the tsunami disaster. We detect other things than earthquakes. We detect blasts, for example. This was a detection. The police called me after a blast in Södermalm in Stockholm and said, did you record this? Could you help us? when did it occur. So we knew exactly where it was. We had a seismic station not far away. We can identify the correct waves on the seismometer, and I can say that, yeah, this blast occurred 0230.3 plus minus half a second. And the policeman said, what? And then it turned out that this guy, this 17-year-old, he had been there. His mobile phone showed that he had been at this address for a minute. So he was very quick in placing it, but he had been there for a minute, which is what then caused him to go to jail. So it's fun. We can sort of help out with these sort of things as well. And of course, you all know that we were the network that detected the Nord Stream explosions on the Nord Stream pipelines a couple of years ago, which of course caused us a lot of media attention. And the automatic detections that we do in the automatic system, so the Nord Stream 1 blast occurred in the middle of the night, 02:03:25, and about half a minute later we actually have the first automatic locations. And similarly with the second one, and also automatic classification, so we know that these are not earthquakes, but they're actually underwater explosions. And finally, landslides. So this is the Stenungsund landslide. Last year, you see the enormous landslide scarp here, and we could actually help the police to say, you know, all these green dots, this is blasting that went on in the last month or two before the slide, and also some timing of the actual when the slide actually occurred. So generally, you know, we get a lot of questions about all sorts of shaking, but I think this interaction between the seismic network and the geophysics community and society is very healthy, and we do feel that we play a role here actually. Thank you. And if there's a question, I'll take that before Steffi says no.
Question? You will probably get my email. Okay, then we move on to our next speaker. Who will pick up seamlessly, but look at Iceland again.
Yeah. Good to see you. My name is Halldór Geirsson, and I'm an associate professor in geophysics at the University of Iceland. And we go back to Iceland, and we'll talk about landslides and retreating glaciers. But really, I guess the theme is climate change, and what effects does climate change have on the solid Earth, linking sort of what both Páll and Rossby have been studying. So there are all sorts of connections here. So Páll was my advisor, along with Þóra Árnadóttir, for my master's thesis many years ago, and grateful for that. So he also taught me some classes in undergraduate study in Iceland, and now he's been retired for some time, but still comes to work almost every day. And we run seminars together and work quite a lot together. So Páll has done a lot of different things in his career, you know, including earthquakes and glacial isostatic movements, which I will talk about specifically, and some other things. So here he is in northern Iceland setting up some GPS instruments to measure crustal deformation. And here he is doing some leveling measurements around Hekla volcano, which is there in the background. And here he is in the Krafla region in northern Iceland. So the Krafla rifting episode was, I think, very influential on his career. And now that we're seeing the current rifting episode on the Reykjanes Peninsula, we draw a lot of learnings from this unrest. And Páll is like a encyclopedia. You can look up in about all sorts of things. And here, just another picture from northern Iceland. He's also a very good guide in all sorts of trips, and it's very popular to get him for all kinds of field trips and things like that as a guide. And here he is in North Iceland on one of these trips. He's also very active in speaking with the media, like he was talking about, and that's very good because he helps, I would say, monitoring agencies to have their finger on the pulse. So if they are not quicker than Páll, then they need to do better. And that's great. And here we are at the university explaining some of the fundamentals of what was going on in Svartsengi already in 2020. So connecting back to Rossby, so towards the end of his career, Rossby went in to study effects of CO2 on the atmosphere. And in this interview in the Time, he says, it would be nice to know when ice will cover our countries again. So he was maybe not looking so much into warming, but well, also would be nice to know when we get covered by glaciers again. We'll see if that, well, we will not personally see if that happens, but at some point in time, perhaps. Okay, so based on these connections, I will do two examples, really, or presentations if you want. I'll talk about something we call glacio-isostatic uplift, and then look a little bit into landslides. So we start with the uplift, and Iceland has some glaciers. They are this white stuff here on the map, and they total about 11% of the area of Iceland is covered by glaciers, and Vatnajökull here is the biggest one, about 75% of that area. And climate has been warming. This is the global average surface temperature over the past 130, 40 years. And we have this overall rise in temperature, and that causes the glaciers to melt, or as we like to say, they lose mass. And the total mass loss is about 16% of what they were in 1890. So it's quite a lot of mass that has been lost. And well, before that, they had been expanding because there was a cold spell for quite a while. And the curve here on the curves on the lower right, they show estimates of how the ice has been melting. And what we see is that, well, we don't have very good information from this time period, but from sort of the 70s, 90s onwards, we have quite good information about how the glaciers have been melting. And we see that during the 70s and into the 90s and close to the 2000s, then some of the glaciers were actually gaining mass temporarily and then losing mass rapidly. And here's just a picture of some of these glaciers. So we have some pictures in mind. This is the southern part of Vatnajökull. And so when these glaciers melt, they have an effect on the solid earth. So when glaciers are melting, we get uplift because of the weight that is removed. And we call this process glacio-isostatic adjustment. So that is the response of the solid earth to these load changes, as we call them. And when we have the opposite, when we have mass gain, then we have subsidence and viscous flow in the lower crust and mantle as a response to that. So when we try to set up some physical models to describe what is going on, then we usually parameterize the models by having some elastic parts and also viscous or viscoelastic parts in the model that have sort of this long-term response. So I'm sure we'll see from Rebekka here more on this. So in Fenno-Scandinavia, there is still ongoing uplift from the deglaciation more than 10,000 years ago, but that part of the deglaciation is all gone in Iceland because of the hot spot. The response, there is much lower viscosity, and the response is quicker. So the uplift that we measure, which I'll show you a figure very quickly, depends on both the ice history, so how has the mass been changing as a function of location and time, we call that ice history, and earth properties, so what is the value of this elastic and viscous parameters and thickness of this elastic part. And these figures here, they just show sort of the effects of having different ice histories on the resulting deformation that's predicted and the effects of the different Earth models, how they affect the deformation. So if there are very, very low viscosities, we get very fast and high amplitude response, and if there's a well, low viscosity all the way around, then we get very small and slow response. So what does the uplift look like in Iceland? It's up to about 3.5 centimeters per year, and this is interesting, I find, because we know that the main plate tectonic movements in Iceland, they're pulling Iceland apart at about 2 centimeters per year. So the uplift is actually faster than the plate motion currently. These are satellite derived figures, velocity scale. You can see that down here, and this is due to the ongoing and recent and centennial, not millennial, mass changes. There are other processes that contribute. There are volcanoes and geothermal areas and things like that, but they are sort of secondary nature in their contribution. We've been doing also continuous measurements over some time. So this is a picture from the Central Highlands of Iceland. We're installing a GPS station here in the year 2000. And the measurements from this particular station are shown here, the vertical component. So since the station was installed, it's gone up by about 60 centimeters. That's something like this. So that corresponds to about 2.7 centimeters per year. This uplift rate is not constant in time. It varies a little bit. It's the slope of this curve tells us how fast the station is going. And it's going a little bit slower. There's like a period where it's going up the fastest. We have many different observations of this from the GPS network and in Iceland. And if we look at some of the data we have from these stations, then in the Central Highlands we have this Skorrakalda station, which I showed you the photo from, and another station here closer to the glaciers. And here we have time series of deformation there and the vertical component. And if we fit lines to find the mean uplift rate for different time periods, we see that it varies quite a bit. So here it's 36 millimeters per year. In the mid-2000s, it's about 22 millimeters per year. And if we take the time period here in the 90s, when the glaciers were growing, remember, then we have only 3 millimeters per year of uplift. So it's very variable in time how much the uplift is. And this is predominantly an elastic response and to some degree viscoelastic response to the current mass changes of the glaciers. And then there are just some more examples. We see this at different stations, not maybe really important for this particular talk. And we can make velocity time series. We can take the displacement vertical time series, and we can take the slopes at different times, and we can plot the velocities and see how the rates are changing. And during the fastest time period after 2010, then we have about 4 centimeters per year of uplift at this particular station. And we can also look at other stations. So this is here in the southeastern part of Iceland, a station called Hub. That's going up slower because that's not as close to the main load. And we find that the velocity there varies from, say, 8 to 15 millimeters per year. Now, interesting thing is that if we look at the east component, so we've been looking primarily at the uplift, but if we look at the east motion of the station, it looks fairly linear on this scale, but if we actually fit the velocities to the same time periods, we get a similar thing. So it's moving a little bit slower east during some times and faster east during other times. And if we plot this together, here the east velocity and the vertical velocity, we see that they're really telling the same story. So when we have faster uplift rates, we have faster east motion, so the station goes faster away. And this is just because glacial isostatic adjustment also has horizontal component of deformation. And it makes a difference by a few millimeters per year. this is something that we have to take into account when we're looking at deformation in Iceland, and also when we are trying to use these models to say what is the viscosity of the upper mantle or lower crust in Iceland. Because we cannot just take any different time period. We have to think about where are we in the glacial history, where are we in the deformation history. And if we so these are all what we call detrended time series. That means some slope has been removed from all of these time series for different GPS stations. And if we take one of these stations that is quite close to the glacier, it's moving slowest in some time period here. And then we can track sort of how it's moving in different ways by sort of, this helps us to see that really we have low speeds in the 90s, we have increased uplift rates in 2000s, and then even more in 2010, and then we have rather high uplift rates since then. So we've been extending this history a little bit by using leveling measurements. So there's a 20-kilometer long lake here southwest of the Vatnajökull Glacier, and there were some leveling measurements made there in 1959, repeated in 91, including well, Páll and others involved in that. And we can use these measurements because we've been remeasuring the same benchmarks using GPS later. So we can make similar sort of velocity plot. So we have here the time scale back to 1959, and the average uplift rate, relative uplift rate between these 2 points is about 4.5 millimeters per year from 1960 to 91. And then it is actually slower in the early 90s than that. It goes down to about 2 millimeters per year, something like that, and then now up to about 10 in recent years. There's a PhD student that has been working on modeling these. We have some previous models. We're making new models now to try to explain this better, why we have these low uplift rates in the 1990s and then fast uplift rates in 2010, etc. And so the climate change, it causes these variable uplift rates, which affects the coastal communities, for example, but it also affects the volcanism. So how is magma in Iceland generated? It's generated by something we call decompression melting. So magma comes from below, it rises under the country, and there is a partial melt that forms by the process as the pressure is released as it goes shallower. So if there's a pressure perturbation when the ice is being removed, it affects the generation of melt down in the mantle. And this can be quantified through some modeling, and this is a time series of the, what I like to call excess melt production in the mantle, and it follows very well the ice history, and shows really that the magma production can be altered by climate change by a factor of 3 under Iceland, which is quite a bit. So some conclusions on that. The GI response in Iceland is highly variable in time, and these glacial mass balance changes, they correspond roughly with changes in uplift rate. So that's the major cause of this. So I promised to talk a little bit about landslides and specifically what are effects of climate change on landslide hazards. And Björn showed a picture here from Stenungsgrund landslide. And we have lots of different landslides in Iceland. This is a map of landslides in the landslide catalog. There are actually quite a lot more, but that's okay. So Páll is the kind of guy always looking at some things and speculating, what is this and what is that? And sometimes he's looking at map. This is from Torfajökull area, and he comes and say, I think I found a new landslide. Did you know there's a landslide in there? And he sees this by looking at these characteristic shapes there. So he has done quite a bit of work on landslides as well. So how does climate change affect landslides? Well, the main trigger of landslide is rainfall. And the climate models, they predict more extreme rainfall events in some areas. So in those areas, we can expect more and more severe landslides. And we have some direct measurements of this in Iceland. These are some GPS measurements over a few days, and scale in centimeters here showing increased sliding rates as we get rainfall of about 150 millimeters over a few days. So we are measuring exactly how this is happening. Climate change also affects landslides through carving out landscapes that are inherently unstable, and then the slopes will fall in. So this is from an outlet glacier called Svínafellsjökull. There's a big crack in the ground there that was discovered several years ago, and this is part of what we think is a pattern of climate change. When the glaciers are retreating, then there is a destabilization of the slope because the glaciers are not sort of pushing as much on the sides there, and they become unstable. And we don't have this landslide failing yet, but there are cracks that are starting to form, and we don't know how far down really the interface goes, but this place has every potential to have a huge landslide or a rock slide that would go on a glacier and possibly into a lagoon and cause a big flood wave to come down. Other landslides, so one here close to the Katla volcano is called Tungnakvíslarjökull landslide. So it's really a whole mountainside that has gone down by about 200 meters. And this is an interesting area. It's close to the Katla volcano, and it's been very seismically active area. And this destabilization, we are sort of debating what is causing it. Is it the thinning of this glacier here, which is thinned by 100 or 200 meters in some places, or is there a cryptodome coming under the slope and destabilizing it? So magma rising under there and destabilizing the slope. So these are things that we can debate what are the sources for these landslides. Last landslide example, thawing of mountain permafrost. So this is a landslide from 2012. Why did it go there? There is permafrost, so ice in the parts of the mountains, and when climate changes, then those masses, which you see here, this is basically a mix of ice and rocks. When that melts, then we get landslide that form as a result of it. So in summary, climate change affects glaciers, it affects uplift rates, it affects landslides, it affects volcanism. And Páll has made contributions to many of these things here, and the uplift rates are variable, and the landslide hazard will increase in many places. So just here a picture of Páll doing some yanka there, but I like to think of science as blocks that we're putting together. We're making all kinds of contributions, and Páll has certainly made many of these block-like contributions to the wall of science, and very grateful to have had the chance to work with him, and hope to work with him for many years to come. So thanks to my collaborators, and thanks for listening.
One quick question while we're changing speaker.
Too shy.
You left them speechless.
Put them to sleep. Okay.
Thank you.
Thank you.
We move to the last but not the least of our speakers, Rebekka, Steffen.
Yes, hi, I'm Rebekka Steffen. I'm a researcher in geodesy at Lantmäteriet. I won't say the long English wordings that Steffi already named for it. So I would like to thank the committee for inviting me to give a lecture here, and also congratulations to Páll for getting the Rossby Prize this year. We heard his name in the previous presentations quite a lot already, and even in my presentation about glacially triggered earthquakes, his name will appear. So he has definitely made a huge contribution to the geophysics world in Northern Europe. So yeah, we heard about earthquakes in the previous presentations, and Halldór mentioned also glacial isostatic adjustment and the relation of glaciers or ice melting affecting the solid earth. And now we talk about the combination of it, basically, glacially triggered earthquakes with a focus in Northern Europe. So glacially triggered earthquakes happen when we have a release of stress along pre-existing faults due to the combination of tectonic background stresses, as shown by the black arrows, and then glacially induced stresses which increase and decrease during a glacial cycle. And these glacially induced stresses have three components. We have loading stresses, which act only in the vertical direction and only beneath the ice sheet itself. And then we have flexural stresses, which come from the bending of the lithosphere that Halldór showed already. And these we have then compressional stresses beneath the ice sheet when we go away from the ice sheet center and towards also behind the ice sheet margin, we get extensional stresses. And the vertical stresses are only existing when we have an ice sheet there. And in contrast, these horizontal flexural stresses are even there once the ice sheet is gone, because we still have the deformation in the lithosphere. And we have even a third component, which is a migration of stresses. When we have a loading, the Earth's the lithosphere mantle system reacts in the beginning elastically. So the lithosphere is an elastic movement, and in the mantle we have an elastic movement. But as loading continues, of the ice load or any load, the mantle starts to behave viscously because the mantle is a viscoelastic material. And while stress is generated in the elastic phase in the mantle, when the mantle starts to behave viscously, the viscous mantle cannot hold the stress in the same way. So stresses are then transformed to the elastic layer left, and which is with continuous loading, the elastic lithosphere. And thus we have also a third stress component of glacially induced stresses, which come from this what we call stress migration. So now we want to analyze these glacially induced stresses. And this we do by calculating the change in column Fayer stress. The column Fayer stress is the difference between the Fayer envelope and the Morse circle. The Morse circle is defined by the differences in the principal stresses, stresses that can come from glacially induced stresses, but also tectonic stresses. And once this circle is below this Fayer envelope, we have delta CFS, change in column Fayer stress smaller than 0, and thus we assume we have stable conditions, and earthquakes are not that likely. While when the circle crosses or touches the line, we assume we have unstable conditions, and delta CFS is larger than 0. And now we want to calculate these stresses, and this is what we do with a glacial isostatic adjustment model. So we use these models not only to calculate deformation of the Earth and accompanying sea level changes, we also use these models that go from the Earth's surface to the co-mantle boundary to estimate stress changes. And these models can come in 1D, in 2D, 3D, as shown here, a Cartesian version, but even 3D spherical and covering the entire Earth. And once we have calculated these stresses and analyzed where we have stable or unstable conditions, we want to compare it to what we know where we have glacially induced faults, which describes the fault movement. And there was a recent compilation of defining new criteria for defining a glacially induced fault. And with this new criteria definition, there's also a compilation of glacially induced fault database. And see who is also a part of this database. Páll also contributed to this glacially induced fault database. So let's look at a few examples of these glacially induced faults in Northern Europe. For the first part, I will show only mainland Europe. You saw these faults in the north by Björn already, and these are clearly identified glacially induced faults. The darker the color gets in this for these red lines, the more certain we are that these are definitely faults reactivated during the last glacial cycle and being a reason of being reactivated by the glacially induced stresses. We also have yellow points, and these indicate us that we have glacially triggered earthquakes happening there, but we cannot clearly say which exact fault it was related to. But we have a few assumptions for some. So let's look at the first fault, which is not too far away from here. So we are somewhere down here, and about 300 kilometers north of us is the Bollnäs fault. This is the first fault in Sweden that was identified with LiDAR data. These data are high-resolution height data provided by Lantmäteriet, and this is a way of knowing where we can have these faults. And this location of this fault is also very close to the more populated area of Sweden. The fault's up here. Not many people are living there, while when we come further to the south, we have much larger effect on the population. Looking at this LiDAR data, well, with a good eye, you can clearly see the faults go up here, also highlighting in red. I'm also showing now a picture in the field, and now you see why LiDAR data were needed to identify this fault, because there is a fault scarp, if you didn't see it. So this was an example of a glacially induced fault in Sweden. Let's moving towards the east, to northeastern Estonia, where we didn't find it via LiDAR data. In that case, evidences were obtained from the analysis of soft sediment deformation structures. And shown by this example here, they have an outcrop with several layers of sediment deformations. And when you're looking in more detail in one of them, you see one of these load casts, and these load casts are an example for something happening in the sediment during the deposition. And in the case of this event, they could exclude a lot of other tremor events, and an earthquake was the only explanation that could have created these structures. So in that case, we also analyzed glacially induced stresses using a geophysical model. And looking at the changing column failure stress now, we're looking for a time from around 20,000, 6,000 years to today. We see most curves lying below zero, so it's stable conditions. While when we move towards the end of the ice, end of the deglaciation phase, we get a change towards positive values. And this is also the time when the sediments were deformed by an earthquake. So the geophysical modeling contributes now to understand this potential earthquake as being a glacially induced or glacially triggered earthquake. Now let's move towards further south, to the southern Baltic Sea, where seismic data were used to investigate offshore faults. And colleagues from Hamburg University identified several faults that dissect the base of the Quaternary and even the seafloor. And here I'm showing you an example of the seismic section moving into the region, or into this part of the seismic, where you can clearly see that the yellowish part, which is the Quaternary, is clearly dissected by a reactivation of a fault which happened quite recently. And also here we also used the estimation of glacially induced stresses to analyze the stability of the fault. And we had many fault points. I will zoom into the same example as I showed you before with the seismic section, and where we could clearly see reactivation. And when we look over the last 200,000 years, we see several phases of positive delta CFS values, so an indication that something happened there. But at one of the deglaciation phases during the last Waxelian glaciation, we have a jump in the change in column failure stress, which points us that an earthquake really happened, that could explain also the seismic section results. And if you now look also at how is the status today, how do the faults behave today, if there are some instabilities, we see that those by red points here, they could be still unstable, where we could have earthquakes. Let's move it further away from mainland Northern Europe. Let's look at other indications of glacially triggered earthquakes outside of this region. But you clearly already see that most of our indications are in Northern Europe, actually. But we see also a few indications in Canada, Antarctica even, and also on Iceland. And there we have the Kerlinger fault, which is a Holocene normal fault. And it's kind of special because, well, in Iceland you would think that, well, you have an earthquake there or you have a fault there, it must be related to the ridge. But this is not a typical fault for Iceland. So you see the Kellinger fault here as a green line, and already with the striking of the fault, you see that it doesn't really fit to the volcanic structures around here. Another interesting fact with this fault is that this fault is on the east of the ridge, and usually these faults east of the ridge should dip to the west. But this fault dips to the east, which is completely opposite. And that's why they studied this fault in more detail and found out that it must be related or could be related to a glacial effect. Going a bit further to the west, now looking at Greenland, there we used a different data set to identify a glacially triggered earthquake. And in this case, we used relative sea level data. These data are used to constrain glacial isostatic adjustment models. They give us indication when sea level was at a certain time. And in case for southern Greenland, around the location of Nanortalik, we have very good data, relative sea level data. And the problem was that when you calculate relative sea level changes with glacial isostatic adjustment models, you want to fit these data and with the curves. But for this region, they were not able to fit data from before 10,000 years compared to data from 10,000 years until today. And they even tried different models, 3D models, different ice models. They were not able to fit both kind of data sets. And so we looked at the stress changes. Maybe something happened else in this region, not only normal rebounding. And what we found that at exactly 10,000 years, we have an increase in column failure stress or an increase in differential stresses, which could point that we had an earthquake at that time. And this is also the time when we have this mismatch between the older points and the more younger points. And then we looked at what kind of offset do we need by an earthquake to move our relative sea level points further down. And we used these estimations to model an earthquake. And we estimated an earthquake, in that case, if it happened in one event, to have a magnitude around 8. But we now assume even that with newer studies that glacially triggered earthquakes didn't happen in only one event. There were probably 2-3 phases where we had these triggered events. And so we used this displacement from the earthquake and corrected our relative sea level data points. And there's something special about this potential fault at the coast of southern Greenland. It's offshore. And if you have an offshore earthquake, we could get a tsunami. So we calculate also the tsunami wave. And now I will run a movie, hope it works, that shows us a tsunami elevation in the first 1.5 days going from this earthquake. And you see that it's not, of course, only Greenland affected by the tsunami, then it's also the coast of Canada, Iceland, and Europe. And if you look at the entire maximum tsunami elevation over 1.5 days, of course, we have the highest waves along the Greenland coast. In that case, we have maximum tsunami elevations of 1.5 meters. You have to multiply this value by at least 4 to get the run-up heights of the wave at the coast, because these are wave heights in the open ocean. And then you have like wave heights of 4-6 meters around Iceland or the European coast, induced by an earthquake south of Greenland. So I want to summarize this now that so we have recent developments. We find a lot of information with geophysical models about glacial-induced faults, and these also help us to understand the evolution of the glacially triggered seismicity. And with this, I would like to thank you for your attention, and I leave you with this picture. You already have seen it, and what I got told is that Páll wants to try to use some supernatural power to stop the lava flow. Thank you.
Questions for Rebekka? You're of course all welcome to email all of our speakers, but thank you so much. So with this, I want to thank all of our speakers from today and everyone also who watched online. It was really very informative and entertaining, partly, but also uplifting that science actually plays such a big role in society, both in a country like Iceland, but also in Sweden. So thank you very much for attending, and see you at the next event of the National Committee. Thank you.
Thank you.